Lecture 11 will talk about the marginal PDF. So last time we talked about the expectation or mean of a random variable x. So this was the slide from last time, so just to remind you that if we have a random variable x that has a PDF little f, in other words it has this cumulative distribution function where this is the PDF, then the expectation basically is defined as the integral over all real numbers, and it has this weight x times our PDF f. And for a discrete variable we have the probability mass function instead, and we have a summation. Okay, so we may have more than one random variable. So we may have several random variables that are associated with the same space. So let's say we have x1 all the way through xn. So we can talk about a multivariant PDF or a probability mass function if we're talking about a discrete random variable. We can define this. So basically, we have x1 and x2 as two continuous random variables defined on some common sample space, having probability measure going from the sample space to 0, 1, as all probability measures are defined. If there exists some function f, which goes from R2 to the positive real numbers, so that we can write the integral over all of R2 is equal to the integral of a, where here a is a subset of R2, which is defined as the space x1 of s, x2 of s, such that s is in or capital S. So this is going to consist of the range of a1 and a2 here that are the ranges of x1 and x2. So if we can write this integral as the integral over a, and we integrate over x1 and x2, and this is equal to 1, then we can call f the joint PDF or joint density function. If also for some subset b in a, we could think about probability associated with x1 and x2 of b is the integral over just b of this joint PDF. So here, this is the way that we define a joint PDF. Basically, you're talking about the probability that you're in some subset B of this range A. Remember, the range has these x1 and x2, and you can write this as the integral over B of my joint PDF or joint density function. So an example with 4 random variables. Let D be the determinant of a matrix, and let's assume that these are random variables. Maybe they're uniformly defined. So these are uniformly distributed on the interval 0 to 1. So here x, y, z, and t are all uniformly distributed random variables on the interval 0 to 1, and we want to find the mean and the variance for our determinant D here. So here our sample space is the 0 to 1 to the 4th. So recall that our expected value is the integral over the real numbers of x f of x dx, and the variation can be written like this. So also we have to remember that on the previous lecture we talked about a uniform distribution on A and B was defined by this. So here, remember, we're talking about uniform distribution on 0 and 1, so this is going to be a 1 and this is going to be a 0. Then for D, we can define E of D as the integral over R4, so 0 to 1, 0 to 1, 0 to 1, 0 to 1. What is our weighting function? So remember, previously, what is our D? Our D is the determinant of this. So our weighting function is going to be determinants found by taking x times t minus z times y. So here we're going to have xt minus zy times our f. So this is our joint PDF. Our joint PDF, remember, all of our variables are uniformly distributed on 0, 1. So this is just going to be 1. So we're going to have just the dx, dy, dz, dt. So if we integrate this, we're just going to get 7 over 72. oh, sorry, we're going to get 0. The variance, we're going to integrate this thing squared, and then the variance is going to be 7 over 72. So we're going to have mean for our d is 0, and the variance is going to be 7 over 72. Okay, we can define a marginal PDF. So this is f sub 1, which relates to the random variable x sub 1. So f sub 1 of x sub 1 is equal to the integral over the real line. Here we take our joint PDF and we integrate it with respect to x2. Similarly, the marginal PDF of x2, we integrate our joint PDF with respect to x1. Conditional PDF. So assume we have a joint PDF for variables x1 and x2, and we have these marginal PDFs, f sub 1 and f sub 2. Then we're going to let x sub 1, capital X sub 1, given the realization x sub 2, denote the random variable where our random variable x sub 2 is defined to be this realization. Similarly, we have this random variable where we fix x sub 1 at the realization little x sub 1. So then the conditional PDF of this random variable, capital X sub 1 given little x sub 2, is given by our joint PDF divided by our marginal PDF f sub 2. And the conditional PDF for our x sub 2 given little x sub 1 is defined as our joint PDF, again, divided by the marginal PDF of f sub 1. So again, just definitions. Okay, so what does it mean for two random variables to be independent? If you have a joint PDF, f of x1, x2, then the two random variables are independent if and only if you can write the joint PDF as the marginal PDF f sub 1 times the marginal PDF f sub 2 for any x sub 1 and x sub 2 in their respective spaces, in their respective ranges. And if this isn't true, then they're called dependent. If you happen to have that they are independent, then here, remember, this is what we defined on the previous slide. This is our conditional PDF here, defined here for our random variables x1 and x2. So here, if they're independent, then this conditional PDF is given by this joint PDF, which now we can write as our marginal PDFs. The f sub 2's cancel out, and we're just left with the conditional PDF x sub 1 given x sub 2. They're independent. So x sub 1 does not depend upon x sub 2, so we can just write it as f sub 1. So for an example, suppose the PDF of a random variable x1 and x2 is given by this value. So suppose we have that it is 8x sub 1, x sub 2, assuming that x1 is less than x2, and they're both between 0 and 1, and 0 otherwise. So the question is are they independent? Are x1 and x2 independent? Okay, so let's first define our marginal PDF of x sub 1. Remember, to find the marginal PDF of x sub 1, we're going to integrate over our real numbers with respect to x sub 2. So here, we're going to integrate over x sub 2. X sub 2 ranges from x sub 1 to 1. So here's our limits. Our value is 8x1, x2. It's 0 otherwise, so this is the only thing we're concerned about. We're integrating with respect to x2. So here we're going to have x2 squared. We evaluated our limits, and this is what we get for our marginal PDF of x sub 1. Similarly, we get the marginal PDF of x sub 2. So now this should be integrating with respect to x sub 1. So this is a typo here. So integrate with respect to x sub 1. X sub 1 ranges from 0 to x2. So those are our limits. We integrate with respect to x1. So here we have this 4x1 squared x2. Evaluated our limits, we get this. So if we multiply our marginal PDFs, we get this complicated thing, which is definitely not what our joint PDF is. So x1 and x2 are not independent. Okay, so suppose instead we have this definition for our joint PDF. Are they now independent? You do the same sort of thing. You find your marginal PDF for F1. So here we have this. X1 goes between 0 and 1. So we just integrate. We get 2x1. F sub 2. We integrate with respect to x1 now. x1 goes between 0 and 1. We have this. We evaluate it on our interval. We get 2x2. We multiply these two together, and indeed we get our joint PDF. So we can write our here we can write our joint PDF as the product of the two marginal PDFs, so they are independent. Now we define the covariance. The covariance of two random variables that are jointly distributed is given by covariance of x1, x2, and it's basically defined as the expected value of x1 times x2 minus the expected value of x1 times the expected value of x2. If this covariance is equal to 0, then they're called uncorrelated. If x1 and x2 are independent, then they are uncorrelated. The converse is not true. So if they're uncorrelated, does not mean they're independent. But if they're independent, then they definitely are uncorrelated. And if they're uncorrelated, then you can find the expected value of x1 times x2. It's just the expected value of x1 times the expected value of x2. So back to our example. We have this example where we had this joint PDF. We already found out that x1 and x2. What is the expected value of x1 times x2? We can just multiply the two expected values together. So remember the expected value of x1. Here we're going to have x times f sub 1. Expected value of x2, we're going to have x times f sub 2 of x. We multiply, we're going to have 2x squared for both of these, integrate both from 0 to 1, we get 4/9. So the expected value of x1, x2 is 4/9. So the next time we're actually going to talk about some coding in MATLAB, which I like, so the smiley face.